before we existed, the graphics was being rendered on a smartwatch on the MCU. The visual quality, as I mentioned earlier, isn't good enough. The performance was not good enough, leading to an overall poor experience to the user. By including our GPU in your SoC, the graphics tasks are being offloaded from the MCU to the GPU, leading to higher quality, I would say, smartphone level visual experiences, whilst also extending the battery life to weeks rather than days.
Hello, IPXers. We're here today, joined by Vasilius from a company called ThinkSilicon. Now, we spend our whole lives talking about these 45 million IoT devices, whatever you like to call them, cars, watches, medical devices, you name it, industrial, existing. You've all heard me say it before, 80 zettabytes of data around the world. Well, in the world of wearables, we've got to have things called graphic user interfaces. And in the world of wearables, we've got to have low power. So these things don't run out of power over 3 minutes. So Vasilius works at ThinkSilicon, and he's going to tell us all about what they do and then how they disrupt the market. So Vasilius, let's just have an introduction to ThinkSilicon first. Mm-hmm. You explain basically what you do, and then we'll ask the big question, which always gets asked: if you didn't exist, what would a design engineer do today? So let's have an introduction first.
Great. Thank you very much, Guy, for the introduction. My name is Vasilis Androtsopoulos. I'm the Director of Product Management.
And I'm glad you said your second name, because we could have been here a long time if I'd been left with that responsibility.
Yeah. It's true. It's true. I was living in the UK for 30 years and I experienced that the whole time. So I'm a Director of Product Management at ThinkSilicon. ThinkSilicon is an applied materials company. I'm looking after the product roadmap at ThinkSilicon and also the go-to-market strategy. So, Guy, ThinkSilicon is a leader in the ultra-low power GPU IP technology for the MCU market. Our company was founded by ex-Atmel leaders, George Sidiropoulos and Iakovos, back in 2007 in a city called Patras in Western Greece. And basically the founders found a gap in the market for an ultra-low GPU IP like our own. The growing market of the battery-powered smartwatch market. At the time, this was not served sufficiently by existing IP technology like MCUs. And the user experience from an MCU was extremely sluggish, and the battery life was also, as you mentioned earlier, not sufficient to last beyond a single day of battery life. The main motivation for our customers, the fabless semiconductors, to implement our GPU in their SoC was to significantly increase the smartwatch device battery life to weeks rather than days, whilst also providing the high quality graphics to this constrained market in terms of cost when driving the display. And fast forward to today, we are now shipping more than 20 million GPUs annually in smartwatches. And we also see a growing trend of other devices, apart from smartwatches, edge IoT devices, which I dub them, things like thermostats, smart speakers, smart, the white goods now, like your washing machines and your... All of these are now requiring displays, and our GPUs are driving those, and the people are wanting to put in those GPUs to drive those type of displays. Okay. So we see a growing need for GPU technologies.
Okay, let's explore that later on in this chat. Mm-hmm. So to be absolutely clear, you're selling IP, intellectual property that sits on top of the GPU that enables extreme low power. I think that was the phrase you used. I think you used the word extreme low power. And then it's the actual graphical interface with the consumer, with the end user. So that gives us a good background. Now everybody listening understands what ThinkSilicon do. So if today ThinkSilicon didn't exist and we were in this market of wearables and we're in this, which we'll come to in a minute, where we've got this things like medical devices or smart consumables, shall we call them, like smart speakers or thermostats. If you didn't exist and a design engineer hadn't discovered Think Silicon, how would they be solving the problem without you today? So that will give us context for this chat. So somebody listening will go, that's me. I should go and talk to Think Silicon. Tell me how they'd solve it without you today.
Okay, so before we existed, again, we are an IP company. We deliver the hardware, and we deliver also all the software for that hardware. Before we existed, the graphics was being rendered on a smartwatch on the MCU. For example, Cortex M4 from ARM or the Cortex M7 from ARM would do the job of rendering the graphics. But this was not good because the visual quality, as I mentioned earlier, isn't good enough. The performance was not good enough, leading to an overall poor experience to the user. And also, the MCU was being utilized to perform graphics. So the utilization of the MCU was very high, and it wasn't able to do other things. And this caused a lot of poor, sluggish performance, severely limiting also the complexity and the quality of the graphics that you could send to the display. And as I mentioned earlier, the battery life also suffered because a GPU is really optimized to run good quality graphics in an optimal way, in a power efficient way. Now, so the thing that we deliver to our partners is we also deliver an API with extensions for 2D graphics, for vector graphics, for 3D graphics. And this actually gets used by our partners in the industry, ecosystem partners. Examples include companies like Embedded Wizard, like Candera. They port those graphics APIs into their software stacks, and graphics developers can go and use those software tools to generate cool graphics, 2.5D watch faces, vector graphics, maps, using those tools and target them on our devices. We also provide our customers a lot of other tools as well to help them to develop graphics for our GPUs.
Okay, so in summary, it would have been, first of all, pretty low grade in terms of the actual interface, in terms of the creativity that a design engineer could bring to that interface. So when their customer is looking at the watch, they're just seeing quite two-dimensional graphics, which aren't necessarily interesting or differentiating, because that's absolutely key, because it's the user experience, isn't it? So there's a differentiation between what the consumer actually sees and how they interact with the device. But then there's also the fact that you're doing it in a different way. So you're not asking the MCU to do everything. So you're able to drive the power consumption right down. Is that, in summary, is that more or less the two big benefits? If somebody were to say, right, I need to understand the benefits, those are the two things that you'd want them to take away from this discussion.
Correct, Guy. Yes, by including our GPU in your SoC, the graphics tasks are being offloaded from the MCU to the GPU, leading to higher quality, I would say, smartphone level visual experiences, whilst also extending the battery life to weeks rather than days. So that kind of summarizes the benefit of taking a GPU and implementing it in your system on chip, as opposed to doing everything on the MCU.
Good. Okay. So let's break that into two separate things. Let's just break it first of all into the graphic interface part. So today I'm not using you. Today I'm using somebody else, or I'm using doing a different method. Just explain how, or the difference between if you weren't there, and then the range of interactivity and the range of differentiation you can offer, and the user experience you can offer if they use your IP instead of what they're using today. So let's just break it into that graphic first part, and then we'll break it into the low power secondarily.
Okay, so so we provide, as I mentioned earlier, a lot of supporting tools and software for the developer to make best advantage of our GPU technology. We deliver a proprietary API for graphics with extension for bitmap, vector graphics, and 3D images. And this is a proprietary driver that we develop ourselves to run any type of graphics on our GPU. And we actually didn't have a choice to use existing open standards like OpenGL or Vulkan, because there is currently no standard graphics APIs that can run on the microcontroller device which is using a real-time operating system or a bare metal. So because we are targeting these tiny devices with very limited memory, we need to develop our own very light API to fully take advantage of the hardware. So we provide this to the developers. We partner with these companies I mentioned earlier, with Embedded Wizard, Candera, MicroEJ, who take these software that we develop and integrate into their GUI frameworks. But we also work with an open source API called LVGL, Little VGL, which is extremely popular with our Asian customers, especially in China and Taiwan. And we are now a partner of LVGL. And we've recently also released a graphics acceleration backend for our NEMA proprietary API for LVGL version 9, and it's available in the GitHub. So any developer, any OEM or graphics user interface developer can download this LVGL port that we've created from GitHub and start designing these really cool 2.5D and 3D graphics for the smartwatch market or for the AGI IoT markets. Okay. So that kind of gives you an idea. We are very tightly knit inside the ecosystem at the moment. There's a lot of availability there for our partners to go and actually develop and do really cool graphics for our GPUs.
Okay. And are there user case studies so they can see a before and an after? So this is an example of where a company, you don't need to name them, but this is an example of where this was their initial graphic output, and then once they started using our technology, they went from there to there. Is there examples of that?
You can, yes. So you can actually take our API, our NEMA GFX, and run it entirely on the MCU. And you can see significantly worse quality graphics when you're running on the MCU. And also the power consumption just goes 10x higher. So this API could also potentially also run on the MCU, but we don't recommend our customers to deploy it for the MCU because it has issues of power and quality, especially for things like vector graphics and 3D as well.
All right.
So, yeah.
So you nicely took us into power there. You'd almost like you'd planned this and you knew what you were going to talk about. So shall we now talk about how you also affect the efficiency of the power with what you do?
Yeah, I mean, the GPU is typically a multi-threaded solution and is optimized to execute graphics workloads and graphics algorithms, as opposed to an MCU, which is a single-threaded solution, which is optimized for single-threaded solution, which does not really fit the graphics type of workload. So that on its own brings a lot of benefits in terms of the power. But we also have dedicated components in our GPU architecture, like the rasterizer block and the fragment core, which is VLSIW. All of these dedicated components are really efficient and fit for purpose for running graphics workloads. That kind of explains some of the power reasons why we get ultra low power. But we're talking about a 2.5D watch face can run in just 2.5 milliwatts of power, which is incredibly little. And that is really our benefit. It means that you can have your GPU displaying graphics always on, and you don't need to dim the screen because the power is so low that you can have it always on and always have your watch face on for days rather than
Okay, so is it fair to say, because you're so clever with how you've designed your graphic interface, it's just a natural outcome? You just create an environment where there is less power being used, or is it the fact that you take you take the responsibility of the power away from the MCU and give it to the GPU with a system on chip. Is it those combination of things, or are you doing something different to create that ultra low power environment?
Yeah, exactly that. It is a bit of both. It is both the architecture of the GPU is designed in a way to take advantage of the specific graphics workloads in a very efficient way. And also everything that comes around it as well. All the software, we have actually tuned the hardware to be optimized for the software that runs on top of it. It's a combination of the hardware and the software that makes the thing run seamlessly and as power efficient as possible.
Right. Okay.
It's not a general purpose, say, graphics MCU. It is a dedicated accelerator for graphics workloads, especially for 2.5D and vector graphics workloads.
Okay, good. So I think that's an excellent introduction. It's an excellent introduction as to if you were, if you didn't exist, how would you do it? And now you do exist. These are the benefits, and this is how you do it for both the graphics and the ultra low power. Right at the start of the conversation, you talked about how it's not just wearables. We're now, we're being asked to go into new markets. So let's just explore some of those new markets now. Explain where you're seeing the use for these, much more intricate, much more user-rich experiences with graphics, and where ultra low power is being used in places other than wearables. Let's just talk about that for a few minutes.
Okay, I mean, usually you would see battery. I mean, the original value for us was the battery powered devices because of our low power consumption, so you can prolong the battery life. But you also see now devices being powered from the main sockets, like thermostats, like washing machines, smart speakers, because we are ultra low cost. We are very, very small in terms of the area footprint. And these devices are now starved of graphics because they don't have the capabilities inside in terms of the cost constraint. They are cost constrained. And so you can see a lot of adoption now of GPUs in those markets. Previously, it wasn't possible because an MCU was all they could fit on the SoC. Now, because the economies of scale are such that you can add more and more bits into the SoC, you can see a lot of those vendors now, SoC vendors, putting in GPUs so they can get that better experience. And the displays are also getting bigger as well. So you can see WVGA resolutions, 800 by 400, screen sizes in the washing machines. People are saying they can, in your washing machine, you can just pull up your entire manual and visualize it, even 3D in some cases. Yeah. So those are interesting new cases where they inspire growth. But I just want to also mention that we started driving functional smartwatches and smart bands. By that, I mean like sport watches and smart bands from the companies like Garmin, Huami, Amazfit, Xiaomi. And those devices were MCU-centric, meaning that the processors were just MCU to do all the main functionality. But now what you're seeing is, of course, the Apple watches and Google Pixel watches and Samsung Galaxy watches have two systems. One is for the big GPU that will download and run the apps, and the other one is our GPU, which is an always-on GPU, to do 95% of all the workloads, like display the watch faces, the notifications, the maps, the video avatars. So there's a new market here for us as well in the advanced premium market, and it's all about the battery life. And the software being developed out there as well, like Google Wear OS is now trying to take full advantage of the little GPU and the MCU, which is on the same chip with a big GPU, to do more functions like notifications, like watch faces, all on the small GPU to save battery. So we see two things. We see an expansion in the smartwatch of expanding adoption in the smartwatch space on our GPUs. So more and more smartwatches are now using our GPU in the premium. And we also see an expansion to adjacent markets for the MCU space, for the likes of what we just discussed, the edge IoT, home. consumer devices that you find in your home because they are getting more rich displays
Right.
and are cost constrained.
Right. So, in summary, if we were, that's quite interesting that you've put it that way, because in summary, we've gone from talking about, I'll try and do this like this. I'll try and be clever with my hands. I'll probably fail, but anyway, that's okay. I'm allowed to fail. You're the clever one on the call. I'm just the person who asks the stupid questions. So you go from very, very low power down here and graphical user interface here. So that's the like deep vertical bit, but then you're then describing how the markets that you're targeting are MCUs over here and GPUs over here. So the overall market, because the way the world is going, MCUs are creeping into where there would have never have been the opportunity to design in really interesting graphical user interfaces, because the chips just weren't capable of doing it. You're saying they can now. So things like washing machines, those sort of throwaway apps that we've been talking about for years and years, but washing machines, coffee machines, all that kind of stuff, smart speakers, you can think about using this kind of technology now. And then you're talking about at the high end, where things that probably you'd have thought would have used too much power at the high end, you're saying, no, hang on, you can start doing that now as well. So in other words, as the world gets more complicated, your market is just growing with it, and your technology, if you like, is slipping very nicely into the future because it was future ready in the first place.
Exactly. That's a beautiful. You couldn't have said it better than myself. What you're seeing is we found a niche in the market, which was the functional smartwatch and smartband. We started with that market, and what you see now is proliferation of our GPUs into new markets. The edge IoT, the washing machines, the power socket markets, and also in the high end, in the advanced market, where there was only one big application processor. Now you see an always-on MCU and GPU there as well, to try and prolong the battery life in those markets as well. And you see a lot of buying from big companies as well, and OS vendors, to try and make this happen in order to prolong the battery life for these small form factors. And also a market that we haven't actually mentioned yet is the AR glasses market. This is a nascent market, and our GPU is a very good fit for this market because of the low power, and because effectively what you want here is someone to be wearing the same glasses that I'm wearing on this call, the same type of weight, and be all day AI. They call them all day AI glasses because it's basically a smartwatch on your face, and you effectively do exactly the same things as a smartwatch, but on your face. And this is like really stretching the bounds when it comes to power consumption. It's another area, of course, nascent. There's no real market there yet, but we are helping for that to become a reality through our GPU.
Good. Okay, so we've done a really good introduction there. We started off with what would you do if you didn't exist? We've then said, okay, you've disrupted that market. So what do you do in order to disrupt that market? And I think we've had a really good, tight summary of that, which is where I started using my hands and trying to sort of work out a way of describing that. So very last question. Somebody's been listening to this. They've been listening now for 24 minutes, which is excellent. So now they've bought into the idea, this could be me. This could be me and my next project. How do they evaluate Think Silicon if they want to start a project next Monday? How do they get hold of you? How do they start playing with you?
Okay, so there are already quite a few platforms out there that you can buy from the likes of Mouser, DigiKey. These are from our partners like Ambic and ST, which have the Apollo 4 Plus out there, and they've recently launched the Apollo 510 as well, which will also be available very soon with our NEMA GPUs. And also ST Micro with STM32U5 platforms. They've got two versions, one that is capable of also doing the vector graphics acceleration. There's a U5A series, is 2.5D accelerator, and also the STM32U5G series. All those are available, and you can buy them, and you can start developing on them using our APIs, and then you can target those already. However, if you want to target our latest GPU, which is the Neox GA100, which is a GPU that's capable of also performing 3D and AI on hardware, then this is still only available on FPGA. So you can reach out to us via our website, and you can ask to purchase the Neox Bits platform, which is a Xilinx-based FPGA platform with a full Linux environment. So you can develop your application on there and experiment on cool 3D watch faces and things like that.
Very cool. Very cool.
And also, just to mention as well, apart from graphics, our latest GPU is also capable of performing AI. It's a GPU, and we've partnered very closely with a company called Edge Impulse, which is a very popular Edge AI platform. And we've integrated our AI SDK into their platform. So any machine learning developer can also pick up the Neox GPU from the Edge Impulse platform and target Neox for AI inference. And that's also something that we've done recently.
Okay, so I mean, the answer to that question is there's lots of options you've just described.
Exactly.
It's almost impossible for if you're looking to do what you described at the start of this interview, and we've now got to the end of this interview, and there are stages of which you might be interested. It strikes me that from the Ambic, from ST, then through to the Edge Impulse platform, through to the Xilinx FPGA platform, you've got about just every software and hardware option covered off. So, Vasilias, thank you very much. This is a brilliant introduction to Think Silicon. We're going to say, what we're going to now say is, thank you very much, Vasilias, and now you're going to say your surname, because I'm going to say, thank you very much, Vasilias, for this wonderful introduction.
Yes.
And I'm going to say your name again, and then you're going to say your surname. So we've got everything covered off so everybody knows who you are. So thank you, Vasilias.
Androtsopoulos.
Excellent. That's it. Covered. End. Brilliant. Thank you very much. Very good.
Thank you very much, Guy, for having me. Thank you very much. Bye.